I said, write down, so give me your claim, H dot, H1, and your test stat. There's a reason why I want you to give me your claim first. Your claim, that's where your mu is, or your P naught is. Does that make sense? So your mu naught or your P naught is in the claim. Your claim is your mu naught or your P naught. And then look through and find the sample, and that is where, in those words, is where you find what your P hat or your X bar are.
Yeah. That's not working.
Well, it's negative, so.
Yeah, I got negative 2. So.
I don't know. I'm going to put it on.
It's the sample.
So then find your test stat. So I feel like people are pretty good, like they think they have this part. We're saying the mean is less than 124. So my H naught is always equals. H naught is always equals, so it should be equals 124. So that tells me that my mean is 124. My X bar is something else. My S is something, and my N is something. Find those somethings. I'm going to plug them in. Oh, and second thing is, find the numerator and the denominator separately. Then divide them.
I know it's correct. Well, the process is right.
All right, so let's see this. My sample of 13 professors, that's my N. Had a mean of 120. My sample had a mean of 120, that's my X bar. And standard deviation of 4, that's my S. So if you plug those in, X bar was 120, S was 4, N was 13.
Yeah.
Oh, sorry. 4 over square root of 13. Find the top and the bottom separately. So 4 divided by square root of 13, anybody have that offhand?
Oh, yeah, I got -0.277.
Oh, before that. The bottom part, and big at the bottom part.
So I got 1.1094 change.
0.94. Great, that'll work. And then if I solve that out, I will get -3 something. Isn't it 3.61?
Yeah.
Okay. That's right. Okay. Good. All right. Has everybody found this? Good? If you did not get this, then you better check in with your neighbors, make sure that you're on board with it all, because this gets a little bit tricky otherwise. Okay. All right, well, you know what, I'll give you folks, I want to need just a minute to check with your neighbors. Can you do that? No? Yes? No?
No, it's fine.
Yeah? No?
No, we're good.
Okay. All right. Okay. All right, so moving on. Michaela, go ahead and read for me.
A type 1 error occurs if one rejects the null hypothesis when it is true. A type 2 error occurs if one does not reject the null hypothesis when it is false.
Great, thank you. So in other words, if H naught's false, then you should reject H naught. That's that top white box. If H naught is true, then you should not reject H naught. Those are all good. Issues occur when H naught is true, but you reject it. So that's that whole thing. Remember when we talked about how a whole bunch of studies are false? Does that make, remember, like they had all these landmark studies in cancer and everything else, and they couldn't reproduce them? It's because you do an experiment, and you know what you think is not true, and you get a normal result. You don't write a paper. So you happen to get an unusual result without knowing it. Then you're like, ooh, yay! I found something, and you write a paper. And it's not that what you're saying is true. It's that you happen to get an unusual sample randomly. Right? We talked about that happening, and the 95% of the time you get a normal sample, you just don't write a paper. So this is kind of this type 1 error it's directly related to alpha, right? It's when you get an unusual sample without realizing it. Type 2 error happens if you do not reject the null hypothesis when it's false. So this is sort of like say my deck really had, the deck I showed you guys really had like 60% black cards, 40% red cards. Everybody with me? It's not 50-50. But when you did your examples, you know, maybe like out of 8 cards, maybe, you know, 8 people drew, maybe like 5 of them were black, 3 of them were red. But the thing is that that's not enough evidence to reject the null hypothesis based on that, right? It's within the range of reasonableness. So it's sort of like this. I'll give you a better example. I'll mention OJ. Always, everyone loves OJ. So here's my rejection range. If I'm right here, maybe it's different. Maybe my mean is different, right? But I don't have enough evidence to say so. It's not extreme enough for me to say for sure that it's different. I mean, I think that, hey, this is the average, you know, what was that, the battery life, right? And then we take a sample and we're way over here, but it's not extreme enough to be unusual. So in a way, you kind of think of this as you're innocent until proven guilty. You're typical, or you're usual until you're proven really unusual. So it's kind of like, it's like OJ, right? Looks guilty, but he's not quite, there's not enough evidence to say for sure that he's guilty. You know what I mean? Well, I was like, yeah, there was enough evidence. So that's the thing. It's like you're close, but there's not quite enough evidence to say for sure that you're guilty. So that's kind of that's sort of the concept is that we require you to be way over here to say that you're not here. Whereas you could totally be, your average could be higher, but it's just not high enough to say for sure that you're different. Is that making sense to folks? So, you know, hey, the average life for a battery is 36 months. With my additive, we got 42 months, but it wasn't enough evidence. I needed to have it to be 43 months before it was enough to be unusual. You know what I'm saying? So that's a problem where it sure seems like it's different. Or like the X-short one, right? 58 out of 100 seemed pretty solid to me. That seemed like a lot more girls than boys. But it was only a z-score of 1.6, not quite enough to make it unusual. So that's this type 2 error where it might be different, but it's not different enough to say for sure it's not here. So that's the type 2 error, is when you're, it might very well be different, but it's not different enough to say that it's to reject the null hypothesis. So this is a type 2 error. And why is it that, there we go, type 2 error. Okay. Type 1 error is this guy here, which we've seen before. Right? You have a whole bunch of samples, and most of them are reasonable, but every once in a while you get a weird sample for no reason. Right? Just randomly, it's going to happen. 95% confidence interval means that 5% of the time you're going to get something unusual. If you happen to get one of the unusual ones, then you're like, oh, yay, write a paper, and actually what you're saying is not true. The mean really is here, but you thought the mean was over there because you got a weird sample. Okay. Right, that's a type 1 error. It's when your sample is randomly way outside of the norm. It's unusual. Okay, the significance level, alpha. You all remember alpha from chapter 7? That tells you how often you should get a weird sample. If I set my confidence level at 95%, 95% confidence level, that means my alpha is 5%. That means 5% of the time I'm going to get something weird. If you folks remember the beginning of the semester, had everybody flip a coin 100 times on your computers. One person or two people had 41 heads or less, and they would write a paper because they were unusual. It's going to happen alpha percent of the time, whatever your alpha is. So typically, our alphas are 5%, but sometimes they might be 10%. If we want to be less certain, or we want to be extra sure, we might make alpha 1%. So, example, when alpha is 10%, that means that 10% of the time you're gonna be rejecting a true null hypothesis because we're setting that level for being, that's our level of unusualness we're setting. All right, so everybody do problem number 5 on your worksheet. What's meant by a type 1 error? What's meant by a type 2 error? Try to put it in your own words if you can. A good answer for a type 1 error. Anyone? Type 1 error? What's a type 1 error? No one? That's like what's written on the paper and you're restating it.
When a sample is taken, when it's an initial sample, it's rare, but it can't include anything because the means are correct. So basically, you just took an unusual sample.
Right.
Oh, the screen's off.
Even though it's corrected.
Ah. All right, is when you took an unusual sample. All right, that works. So type 1 error is when you took an unusual sample. So you thought your mean, we'll say mean because it's just easier, then was different when it isn't. Okay, that's good. Thank you. How about type 2 error? Not the thing from the book, something else. Anybody have, yeah, go ahead.
I put when there isn't enough evidence to reject a truly false null hypothesis.
Ah, I like that. So you reject a truly false H naught. In other words, when it's different, but it's not different enough, right? So it's different, like you said, but it's not we don't have enough evidence. It's not different enough to be to match up. Okay, good. All right. So next we're going to talk about the critical region or rejection region. So that's the range of values of the test stat that are unusual. So we would reject the null hypothesis. So over here, this is the rejection region. It's unusual. All the stuff over here is not the rejection region. It's not different enough. It's not unusual. You're putting this into your notes, I believe. Move this over. All right, so the critical region, that's this where you're far away from. Remember, H naught is right here. So if I get anywhere in here, then I'm like, okay, H naught might be true. That's the non-critical, that's the non-rejection region. If I get something way out here, I'm like, oh, that's weird. That's unusual. I'm going to reject H naught. These two areas are split by my critical value. Where my critical value is sort of it's the z-score between the unusual and the usual. So the unusual and the usual. Where do we get the critical value? From the table. It's the exact same critical values that we used in chapter 7. We'll use the t-table for means. We'll use the z-table for proportions. And you'll see if you look at your t-table, not the confidence interval row, but the next two rows down at the top is for one-tailed or two-tailed tests, because they're a little bit different, depending on whether the alpha is split in half or not split in half. Okay, good. Everyone's filled in their notes?
No.
Okay, no? Fill them in, or take a picture. Moving on in like 5 seconds. The critical value, this is also in your notes, it's the z-score that separates the critical region from the non-critical region. Again, it's based entirely upon alpha, just like it was in chapter 7. And you can, and then this is also in your notes. You find the critical value by, if it's one-tailed, inverse norm of alpha, and then pick the correct sign, right? If it's left-tailed, make it negative. If it's right-tailed, make it positive. If it's two-tailed, then do inverse norm of alpha over 2, and you're going to have a negative and a positive, because your alpha is split in half. However, as you'll see in your notes, it's a lot easier to just look it up in the table. These are for z-scores, right? So z-scores are for what? Proportions or means? Proportions, easy peasy. Proportions, z-scores. So remember, here's my t-table. Everyone look up. Here's my t-table. These are all t-scores up here. The very bottom row is z-scores. I told you you can even write z-score right here next to it. Just the bottom row only, those are z-scores. So you no longer need to use a table in your notes. You can just use this handy-dandy sheet. It's got everything. It's got the z-scores you need down the bottom row, and it has all the t-scores above. So just use for z-tables, use where my degrees of freedom is infinity, those are your z-scores. Everybody on board? Way easier than this whole inverse norm thing and do I divide it in half or not divide it in half and this whole nightmare stuff about that. Oh, yeah, it's okay. We'll come back to it. Here. P-values. All right, so try to look over here if you can. The p-value is a probability of getting a test statistic at least that extreme. So in other words, remember I had you folks do that whole flip a coin 10 times, right, and then figure out the probability of getting 9 out of 10 heads, and we came up with like 1.1% or something like that. That's the p-value. Now, what's the probability of getting 9 out of 10 heads? So the p-value is the probability of getting your sample, and what's our general guideline for unusual?
5% or less.
5% or less. So you get if it's 5% or less. In other words, if it's less than alpha, if it's equal to or less than alpha, it's unusual. If it is left-tailed, it's the area on the left side of the test stat. If it's right-tailed, it's the area to the right. And if it's two-tailed, you have to double it. It's kind of weird. We're not going to deal a whole lot with p-values, but who here is taking an ology? Biology, psychology, sociology, right? So in those classes, you're mostly going to use p-values for any of your hypothesis tests. And so you find out what the p-value is, and you'll compare that to alpha. Generally, alpha is 5% or less, so you'll say if it's 5% or less likely to happen. If your p-value is 5% or less, 0.05 or less, you're going to reject the null hypothesis. Or whatever your alpha is. You might set your alpha at 10% or 1%, something like that. Right, so in other words, the null hypothesis is rejected if your p-value is less than or equal to alpha, if it's unusual. Left tail test, you'll see here. Let's see, here's my test stat. So here is the area in the tail of the test stat, and you'll see that in blue, and you'll see that that is 0.032 less than alpha, right? Here's alpha, and it's less than that, so it's clearly in the rejection region, so I'm going to reject. That makes sense. Likewise, here's another example on the right-tailed side. So here's my test statistic right here in the do not reject region. And if I look at my area and its tail, my p-value, you'll see my p-value is 0.064. More than alpha. Alpha is 5%. So totally not unusual. Do not reject H naught. Okay. And then we get these weird two-tailed things. It gets a little bit strange. Here, you look at it. Here's my p-value. My test stat is not is in the do not reject range. Everyone see that? But if I look at this p-value, if I look at the area in this tail, it's 0.032, which is less than alpha. So why am I not rejecting H naught? It's two-tailed exactly. So my alpha is split half on the left and half on the right. So it's not really fair to compare my p-value to all of alpha. I should only compare it to half of alpha. Does that kind of make sense? So what I need to do, if I want to compare it to alpha, I need to double it. So I'm making an imaginary one on this side so it can compare to alpha properly. But rather than make you folks decide about like, do I double it? When do I double it? Whatever, then we're not going to really find p-values you're doing the inverse norm way and stuff like that. We're just going to use our calculator tests, and that will give us the p-value, and we're just going to find it that way. It's just messy and murky and really serves very little purpose, except for confusing people, which there's enough confusing stuff that you need. I don't need to add more stuff that's really not useful. Okay. Here's an example, right? Our X sort. Remember how I kind of thought it was kind of unusual but not enough? I had a test stat of 1.6. So if I were to do, let's see, 1.6. Here's 1.6. And I found the area in this tail. How would I do that? I would do normal CDF of what? Anyone ever remember this? I want this.
It's 1.60,
1.60, comma, infinity. Yeah, sure, that's close enough. And I would get 0.0548. Everybody on board with that part?
Yeah.
Is that unusual? If our alpha is 5%? Is this 5% or less? No? So it's not unusual. Does that make sense? And we would not reject H naught, which is what we found earlier, because 1.60 we said we would not reject H naught there either. Though, I mean, I feel like it might be true, right? It could be true, because it definitely is high. 58% is certainly higher than 50%, but it's not, we don't have enough evidence. Does that make sense? So it's a type 2 error, maybe type 2 error. We wouldn't have enough evidence to say for sure. But if my alpha is 10%, then it would totally be unusual then, if I changed my alpha. But if I made the requirements less stringent. Okay, we are going to not do this one yet. We'll do it later. So I think we'll stop there for today. You folks out a little bit early. I'm going to hand out the exams.